Hello everyone, thank you for coming to my presentation. I'm Yang Zhang, a PhD student from University of Connecticut. So my presentation title is Deterministic Optimization for Damage Identification using Dividing Rectangles Algorithm. It is co-authored by my advisor, Dr. Tang. The presentation includes following sections. So the first section is the background. Nowadays, ultrasound probe is used to do the railway track monitoring, but this kind of method has some limitations, such as the low efficiency due to the slow working speed, intense labor, and uncertainties involved. So what we want to do is to explore and develop a new technology with high efficiency and robustness in damage identification. It integrates piezoelectric transducer, inverse analysis, and sensor techniques to achieve the damage identification. So the damage is defined as changes to material or geometric properties, or changes to boundary conditions or system connectivity. And there are several techniques for structural damage identification, such as structural vibration, electromechanical impedance, AUT. And this table just compares these 5 techniques from different aspects, like frequency range, actuation approach, etc. And here in this research, we used admittance-based methods because it is highly sensitive to damage by using high frequency with small wavelength. And that damage can result in admittance change around the resonance frequency, and this admittance change can be used as damage indicator. And these two pictures are the PZT system. The PZT is installed on the top surface of the host structure. The first picture with input as voltage, and second one, the input is movement or vibration of host structure. And in this kind of system, the PZT can convert electric energy to mechanical energy and vice versa. And in the PZT system, the impedance is defined as the ratio of input voltage to the resulting current, and admittance is the reciprocal of impedance. So, and when we get the admittance, it contains information related to vibration of host structure. It means when there is disintegration damage in the host structure, it will be reflected in the admittance curve. So as shown in the bottom picture, due to the damage, the admittance curve has a shift around the resonance frequency. The difference between the two curves is called admittance change. So now we can know that if we introduce a damage into the host structure, we can use the finite element method or experiments to measure or observe the responses of admittance. But as we will know, in the practical engineering, we can only get the responses, but do not know where the damage is and the severity of damage. So this is the inverse process. With all this in our minds, we now give our summary of motivations. So here, the data will be used in this method is admittance change from finite element or experimental methods. So as we said before, the damage identification is an inverse process, and the inverse problem is always ear-post problem. They are not of answers. So we convert it into an optimization problem and using the dividing rectangles algorithm to solve it. So the goal we want to achieve is to obtain multiple solutions, and based on the engineering judgment, to select one true solution that identifies the damage location and severity. So now we give a simple introduction of PZT admittance model. So for the coupled system, we have the coupled governing equations. By using Taylor series expansion, we can get the admittance change. So as shown in this picture, when there is damage, the admittance curve will have a shift around the resonant frequency, and we can get the admittance change in that shift area. But in most cases, the inverse problem is undetermined or ill-posed, or it means that the useful admittance changes are far less than the unknowns. So as shown in the picture, the shift area is limited. The inverse problem is undetermined, so it is challenging for us to do the matrix inverse operation. Then we cast the inverse process into optimization problem. So by formulating a multi-objective optimization problem, we can obtain multiple solutions and then select the solution according to the engineering judgment. At the same time, we could avoid selecting the weights for different objective functions. So this presentation formulates the optimization model targeting difference in admittance change. And because there is only a small area having damage, so the damage index vector is sparse, then we formulate the second objective, the zero norm, to determine the sparsity of damage index vector. And then we use dividing rectangles algorithm to solve it. The algorithm has three advantages. Since the objective function is a black box, there are many local minima, while the direct can search the space and always find the global minimum. And another one is the deterministic property. It means that the algorithm can obtain solution by running only once, compared to most of stochastic optimization algorithms. In addition, there is fewer parameters that need to be tuned for the algorithm. Direct algorithm includes main four steps. The first step is the normalization. The algorithm will transform the searching space into a rectangle, cube, or hypercube according to the dimension of the problem. And then it is the sampling and division. Sampling means calculating the objective function values at the center of the rectangle or cube. So as shown in the equation 2, mu is the 1/3 of the side length of rectangle. So by comparing the minimum objective values, we can conduct the next division at the corresponding rectangle. But one thing is that how we determine which rectangle is potential for division. This is step 3. The ith rectangle is said to be potential. It should satisfy the two conditions, the equation 4 and 5. The k and epsilon are constants. F and n is current minimum. So if the ith function value fci satisfies the conditions, then the ith rectangle will be divided in the next iteration, and then repeating steps 2 and 3 till the maximum iteration is reached. A direct algorithm is initially developed for single objective optimization. Here it is developed to solve the multi-objective optimization problem. So firstly, non-dominated sorting algorithm is introduced. We use non-dominated sorting to rank the solution with different ranks, or 1 or 2, and so on. So as shown in the first two pictures. Then the jth rectangle is said to be the potentially optimal by satisfying the condition 6. So in equation 6, R is rank operator, D is the longest length of rectangles. Thus, the algorithm can group more rectangles with same size at the same time. So in this development, the condition equation 5 in the third step can be omitted due to the condition 6. So as shown in the third picture, the yellow solid circles have same rank, but the left one has smaller d, so the left one will be ignored, and the right one will be archived as the parallel front. Another development is the sparse exploitation. So as shown in the bottom picture, firstly we calculate the objective function at center C1 and then ignore the C2 and C3 simultaneously. But if there is no improvement at C2 and C3 when exploring, thus due to the deterministic property of the algorithm, it will stop after certain numbers of iterations. So the center vector C1, C2, C3 till Cn will have many zeros entries, or it is a sparse vector. So if we can know the sparsity in advance, then the algorithm can change the searching space and improve the computational efficiency. Thus, the second objective is build a zero norm of damage index vector. And this animation is showing how the algorithm works. So now we use 3 different cases to verify the proposed multi-objective optimization-based framework for damage identification. So firstly, the cantilever plate is divided into 25 segments, and we define the damage location and severity as shown in the pictures. So there are 3 different cases with 1, 2, and 3 damage locations. So by solving the optimization model, we obtained the identified results as shown in the figures. We can see that the algorithm identifies damage and location and severity at the same time. So without loss of generality, here we use the third case to elaborate how the algorithm works. This table lists the obtained multiple results. We can see the smaller residues have more predict segments, and the results 3 to 7 are similar to each other, as shown in the 5 pictures, and we can select one solution based on engineering judgment. Similarly, we studied the 2 cases using experimental data. So we introduce a damage at the location 12th and 14th segment with different severity, and then we obtain the multiple results for the 2 cases. So as shown in the figures, we can see that obtained solutions show trade-off between objective 1 and objective 2, and there is always one solution with high precision in the parallel set. In all these cases, note that the identification errors may be caused by the linear approximation in analytical expression and modeling, and as well as the measurement noise. But identified results agree well with the true damage location and severity. So let me conclude my talk by summarizing what we have done. So by converting the inverse process to the optimization problem, the difficulties in the inverse problem is tackled. And by using multi-objective optimization, we obtain the multiple solutions. And based on the engineering judgment, we can always select one solution that identifies location and severity of damage. And this method can be applied to different structures like the plate, truss, and the railway track, etc. And for future works, we are going to deal with the modeling uncertainty and measurement noise. Thanks for the funding for this research, and thanks for your listening. Thank you.